So here are the notes for week 10, and we're going to be doing two major things. This is notes for exam 3 on Tuesday the 11th. So there's two major things, but oxidation reduction and then balancing of two specific types of reactions, combustion and acid base. So first thing we're going to look at is oxidation reduction reactions. And before we even do it, I'm going to mention sort of a saying that has helped me, and really I think every chemistry teacher teaches this, uses this or some sort of it. So we have this guy here in the middle. He was in Fight Club, he was in Avengers, Frozen, Mona, Zootopia, Barbie, Minions, Spider-Man, No Way Home. You might, so it's obviously it's Brad Pitt, and Brad Pitt is saying grr, so I don't get what Leo has to do with that. But if you lose electrons, you become positive, and if you gain electrons, you become negative, because electrons are negative. You lose something negative, you become positive, and if you gain something negative, you become negative. And so Tom Holland here is saying grr, and you gain something negative, you become negative, and you're reduced. So here you lose something negative, you become oxidized, gain something negative, you become reduced. Alright, so here's an example of an oxidation reduction reaction. We have copper, so Leo, loss of electrons positive, gain of electrons negative. We have copper going from +2 to 0, so we know that that is going to be reduced. We have magnesium going from a 0 to a +2, that is going to be oxidized. And you have one here, or just again, I guess referencing Leo says grr. It's the same reaction we did. So just to revisit the rules, oxygen is always -2, but it's in group 16, so that makes sense. The O2 is a 0. Hydrogen is always a +1, but it's in group 1, so that makes sense. But H2 is a 0. Just like F2 would be a 0, the Cl2 would be a 0, and just like Na would be a 0, and Mg would be a 0, and N is 0, but I don't think, yeah, that'll be N2. Anyways, but if it was by itself, it's going to be a 0. Group 1 elements are +1, group 17 elements are -1. Polyatomics sometimes need to be broken up, but we'll do examples that show that. So I'm going to try to solve these by setting them up algebraically, which is not something I did in class, but might work for people. So there's no charge on that first one. We know chlorine is a -1. And chlorine's a -1 because it's in a compound, so it's not 0. And then it's in group 17. So if we're to solve for copper here, we can go Cu plus 2 minus 1 equals 0, or Cu equals plus 2. And the next one, we know oxygen's always a -2. Hydrogen's a +1, but let's just prove that algebraically. Hydrogen's a +1, oxygen's a -2. So if we go +1 times 2 plus a -2, we do get 0. Then when an element is an ion, the element is just that ion charge. If an element is alone, a diatomic, it's 0. So I'll set up this one again algebraically. NH4 plus equals 0. Hydrogen's +1. So, my bad. So if we set up algebraically, then NH4 would have to equal +1. So I take that plus and I put it on the other side algebraically. And then that hydrogen's a +4. So we have nitrogen plus a 1 times 4 plus a 4 equals a +1. And so nitrogen is going to be a -3. Because if we subtract 4 from both sides, that's what we get. Next one is a lone ion. So it's that charge of that ion. Last one, oxygen. And I'll do that V2O5 algebraically. So V2O5, there's no charge on that ion, or there's no charge on that compound. Oxygen, so like 2 times V minus 10 equals 0. So oxygen's a -2. -2 times 5 is a -10. So 2V equals 10. So V must equal +5. Here we have a 0. I'm just going to do the third and fourth one real quick. Sodium, it has a +1 ion on it. So it's +1. That oxygen is always a -2. Hydrogen is a +1, which makes sense because we add those up, it's going to add to a -1. So the best question on here is the Cr042-. And algebraically, if we set it up, all that has to add up to a -2. So oxygen is a -2 always, so that makes that a -8. And if we added up those in the compound, what would chromium have to be to make it a -2? Then it's a +6. And therefore, all those elements would add up to a -2. Now, I think we do them later, so I'm not going to do one now. But they get slightly harder than that, but not too much harder. But I'll do one later in the slides. The last one on this example is probably the best one. So if we set it up algebraically, we know that HCO3 equals a -1. If oxygen's a -2, it's at a -6. If hydrogen's a +1, it's at a +1. And all that is equal to a -1. And then carbon is going to be whatever that number is. And I don't know how you do this, like, or what your teacher would say if you'd solve one side. You add 6 to both sides, and then subtract 1. So this is going to end up being a +4. So carbon equals a +4 here. So quickly, I'll do the 2 in the middle. I guess the bottom 3. Silicon's going to be a +4 because oxygen's a -2. silicon's going to have to cancel out 2 oxygens. The elements alone, it's always 0. Then oxygen is always a -2, hydrogen is a +1. Algebraically, that makes sense because there's 1 of each, equals -1. But that top one is the best one on here. Fe2O3 equals 0. Oxygen is a -2, so it's essentially going to be 2 irons plus a -6 equals 0. Or 2 irons equals a +6. So Fe in this, so I guess divide both sides by 2. So Fe is going to be a +3. Because oxygen is a -2, that would make sense because 2 irons cancels out 3 oxygen. Just to go back to the rules, we have is always -2, but O2 it's 0, hydrogen +1, but as H2 is 0, lone elements will always be 0. If they're charged, it would be the charge element. Group 1 elements, so like lithium, when in a compound, I guess I should say. So like lithium in a compound, or sodium in a compound, or potassium in a compound, it's always a +1. Group 17 in a compound, it's always a -1. So we have 2 chlorines there, so that magnesium is a +2. So KCl, this is a good example in the sense that potassium is always a +1, because we say there that group 1 elements is a +1, and then chlorine is a -1. Polyatomics, we're going to review more in the next section. So this slide really is a test to whether or not you understand oxidation numbers. So we have this and this, and we're sort of ignoring everything else because, well, hydrogen's always a +1, oxygen's -2. Hydrogen's +1, oxygen's -2. So maybe even if we look at that H3O plus, that makes sense where hydrogen is a +1, oxygen's a -2, and you have 3 hydrogens, that's gonna equal a +1. But the harder one of this, or at least that was good for understanding. But here we have CrO4 2- on the reactant side, and on the product side we have Cr2O7 2-. So if we set this up algebraically, both will equal a -2. Then oxygen is always a -2. So on the reactant side, we can put a -8 because there's 4 oxygens. On the product side, we can put a -14 because there's 7 oxygens. And on the left side, or the reactant side, what must chromium be to equal that -2? And chromium will have to be a +6. Then on the product side, because it's a +6 as well, if we add that 14 to both sides, that equals a +12. So we can go like 2x equals a +12. and X equals a plus 6 as well. So like here, that's going to be neither. So minus 14, so I'm looking at I'm just going to check that in my head. Oxygen's minus 2, so that's negative 8. So chromium has to be a plus 6. Product side, negative 2, negative 14. Overall is a minus 2, is 2 chromiums plus 6. So that's neither. So that's a good question in the sense that it's neither oxidation or reduction. But I mean, if you can figure out the oxidation reduction numbers for that, you know, you're in good shape. And we have this next one, CH4. And then CO2. We can set that up algebraically, both equals 0. There's no charge on it. On the reactant side, plus 1, so plus 4. What must carbon be to equal 0? On the product side, we have minus 2. What must carbon equal to make that 0? And then on the left side, carbon would have to be a minus 4. And on the product side, carbon would have to be a plus 4. So I think for these, you know, that practice that you can get with your homework over and over by just try another example or practice, makes these a lot easier. So here we go from minus 4 to plus 4. We go Leo, loss of electrons, positive, Ger, gain of electrons, negative. We're becoming positive here, and so this is going to be oxidized. So both of these here have good examples. We got this on the left. Na2CO3. We should break down that polyatomic, and you can solve it two ways really. So I'll solve it both. Sodium is a plus 1 times 2. We got a plus 2. Carbon we do not know. Then oxygen is a minus 2, which makes it a minus 6. That has to equal 0. And so carbon is a plus 4 in this situation. Otherwise, would break it down into the polyatomic, where oxygen is minus 2, that's a minus 6. That all equals 2 minus. So again, carbon has to be a plus 4. So neither oxidation nor reduction happens for this reaction. Then we have the copper chloride above. Where on the left, chlorine is a minus 1. That's in group 17. That makes us a minus 2. Copper has to be a charge to make that 0. So copper is a plus 2. Then CuI, iodine's minus 1. So copper has to be a plus 1. So it's becoming more negative. And we can again go, if you lose electrons, become positive. If you gain electrons, become more negative. And so this is reduction. As for this last one here, we see Cl minus is a minus 1. We're ignoring the coefficient in front. Cl2 is a 0. So loss of electrons, positive. Gain of electrons, more negative. Here it's becoming more positive. So this is going to be oxidized. For determining which reactant and which product, or I'm sorry, which reactant is oxidized. Iron is alone, so that's a 0. Copper, Cl2, -1, -2, so copper is a +2 on the left because this equals a 0. And on the right, FeCl3, -1, that makes this a -3. So iron has to be a +3. Chlorine's a -1, copper's a 0. So iron is going from a 0 to a +3. So iron Fe is oxidized, and then the other one is being reduced. This one right here, where AgNO3. NO3 is a polyatomic with an overall charge of -1. So Ag is a +1. Copper is a 0. On the product side, Ag is now a 0. Copper is a +2 because NO3 is a -1. So Ag's becoming more negative, so it's reduced. So I'm going to write the whole thing though, AgNO3, and then copper is oxidized because it's becoming more positive. Now we're going to learn how to balance two types of equations. One is combustion, and then acid-base. Combustion is the opposite of photosynthesis. So like in photosynthesis, plants take in carbon dioxide and water, and they produce food, like sugar and oxygen. And energy, like the sun, is on the reactant side. Combustion is the exact opposite of that. And why we balance equations? Well, you can't create nor destroy matter. But stuff on this slide I generally won't ask. So if we look at this equation, on the left we have 1 carbon, 4 hydrogens, and 4 oxygens. On the product side we have 1 carbon, 4 hydrogens, and then we would have to add up these oxygens. We'll get 4 because CO2 has 2. Then if we multiply that 2 in, we have H4O2. We can add up those oxygens. So a 2 at the front would multiply in and contribute to the total amount of hydrogens and oxygens. Two waters is, you can write it also as H4O2 when balancing equations. Let's hear how then heat or energy is produced in combustion reactions. So just like energy is needed for the reverse reaction in photosynthesis, energy is produced in the combustion reaction. To balance combustion reactions, you can follow the formula of CHO. We have a carbon-based compound, we have an oxygen, and you always know it's going to produce H2O and CO2. So first we're going to just write in so I multiplied that 2 in to those, that 3 into those. I got C3H6O2H2. So I'm just going to rewrite that a little bit better. We know it reacts with the oxygen. It forms water and carbon dioxide. And so if you balance carbon first, 4. Balance hydrogen next, 4. And then balance oxygen last. Now here's one where oxygen is in 2 places on the product or on the reactant side. And so on the product side we have 4 plus 8, 12. We have to make the reactant side 12. And here it's going to seem hard because you have an oxygen in the carbon compound and an oxygen that it's reacting with. But if you just subtract those two, then we can balance it. Nope, that's not a 6. And so if there is oxygens in the carbon-based compound, you can subtract those, get a number, and then put in front of the O2 whatever number you need to balance the equation. Here we have another example of C6H6 plus O2. This, notice how there is no it forms carbon dioxide and water. Doesn't matter which order we put those in. We're going to balance carbon first, then hydrogen. So you can think of it, you just put that number there and take this number, divide it by 2, and put it there. And then we're going to balance oxygen. And on the product side, we have 12 oxygen plus 3 oxygen, that's 15 oxygen. We have to put a number in front of this O2. You can't put a whole number because you have to get that to 15, so you can put 7.5 and 1. After you do that, you can't have a fraction in the balance equation, so you're going to just multiply everything by 2. So another we have here, C5. This one is sort of a headache. I'm going to rewrite this just to C6 H12O plus O2 forms CO2 and water. Balance carbons. I'm going to balance hydrogen. And then I got 12 oxygens plus 6 oxygens, that's 18 oxygen. And lastly, I'm going to balance oxygens. So this one really is a tough one in the sense we have an oxygen in the carbon compound, and so we're going to just subtract 1, we're going to get 17, and we have an O2 there. So we have to put a number, and at this point it would be balanced. Again, you can't have a fraction in that number, so you're just going to multiply everything by 2. And you're never going to have to multiply it by 3 or 4 or something. It's always just by 2. So this ends up being 2C6H12O plus 1617O2 forms 12CO2 and 12H2O. Your homework, I don't know. I don't know if they'll take that C6H12O. Oh no, they already have it written for you. So you just have to put a 2 in front of that. And so 217, 12, 12. That's if you were trying to balance that by yourself without using some sort of method, that would just take forever. And now we're going to balance some acid-base reactions. An acid has a hydrogen in front. The base ends with OH. And when the two react, you're always going to form water and whatever is left. So first goes with second here, NaCl. So water and a salt, or water and an ionic bond. Here are just some examples of acids. Here's some examples of bases. So in a sense, water is both an acid and a base. But since it's equal amounts of acid and base, it neutralizes itself. Something that we'll learn soon is it then has a pH of 7. So we already did this one. But let's look at an example. We got HBr plus calcium hydroxide. OH is always -1. Br is -1. Hydrogen is +1. Calcium is in group 2. We know that it's going to form water and then whatever is left. Since calcium and bromine bond, it has to be CaBr2. And so this is the reaction that occurs. There's a 2 outside that hydroxide, so we know we have 2 OHs on the right as well. And then there's a 2 there outside bromine, so to balance it, we're going to go back to the other side. And if we look at all the possible ones that we can get, it's always going to be a 2. And for your homework, you're going to have to write H2O. This one is a little bit easier in the sense that it's already going to be balanced, but there's also a polyatomic ion involved. Nitrate, if you look at your polyatomic ion sheet, is a -1, just like hydroxide, and then sodium is in group 1. So that H and that OH form water, and then first goes with second here. And this is already balanced. There's no numbers outside this parentheses of OH, and NO3 is the same on both sides. So you got to think of polyatomic ion as something individual. These are all really as close to as many as there are. If there's any other one, you would mimic one of them on here. So like I don't see a couple, but really you can balance these, you can balance any of them. And I do give that answer key in a couple slides. So here's that key. That's how it always forms water. And then the salt, or the second one, the first one. And you can see a pattern here. The 2 outside that, so you're going to put a 2 there. Or if you have 2 outside that hydroxide, you can put a 2 in front of the water. So there's definitely a pattern. Now, you'll have to do a reverse reaction where you notice water is formed and a salt is formed. So that means an acid and a base had to form it. And first, inners and outers, I guess one can say, inners and outers, where the first one is always first and the on both, for both of them. So like K and OH and H and I. And smart thing to do is just to write above what the charges are. Potassium is always +1, iodine -1, hydrogen's always +1, hydroxide -1, because that is in group 1, is in group 17. Hydrogen's always a +1, hydroxide always is a -1. This one is definitely challenging. Where I think it's almost needed to write the charges of each above. Barium is in group 2. Nitrate is always -1. Hydrogen is always a +1. Hydroxide is -1. So for the products, maybe the easier one, the acid, because H is a +1, NO3 is a -1, so inners with inners, outers with outers, and we got H, NO3, then outers with outers, but here, since barium is a +2, it's going to need 2 hydroxides to cancel it out. Now here, we have 2 hydroxides, so we're going to have to put a 2 on the right side. And then if there's a parentheses on the right side as well, we'll have to put a 2 in front of wherever that is. And so when you're balancing these, look for parentheses. If there is parentheses, go to the other side and make that work.